So, welcome everybody to IPAC 2026. We have an exciting lineup of lectures this year. Starting off will be Alessandro Aracci in joint work with Paolini and another collaborator. And what they did is prove a rise version of the irrational version of the rise version of the delta conjecture. So Uh, I might mention that back in the day when, shortly after the Delta conjecture was formed, Garcia and I spent some time trying to extend it to the rational world. He was into that stuff with Francois, but we failed. We found a way to do it with when Q is one, but we could never figure out how to do it. But anyway, Alessandro and his collaborators have done that. And so that's a significant advance in this general area. And then later in the summer, Brendan and Andy will be talking about their recent proof of the Fields conjectures with one of their collaborators from Japan. Okay, so if you haven't been here before, the format for IPAC is different from an ordinary seminar because we have each like 6 lectures or so on each paper, and there's no time pressure at all. So feel free to interrupt, just unmute yourself and throw out a question at any time. We can stop to discuss things without any hurry. Okay? So without further ado, we'll turn it over to Alessandro for the first talk on the Falls decorated rises version of the rational theorem. Okay. Thank you.
Well,
Go ahead, Alessandro.
thank you for having me here. I really like this series of seminar because as you said, there's no time pressure at all, so you can really go into the details of everything. And I think it's very, very useful to have someone actually explain their work rather than just giving a short talk or reading the paper. I think it's very, very helpful. So I'm very glad to be able to partake in this initiative. And yeah, of course, I second that. If you have any kind of question, any remark, anything, just interrupt me, and I'll be glad to expand, explain, whatever you want. Okay. So I assume that most of the audience is familiar with this story, like the shuffle theorem, the delta conjecture, and all the advances in the area, but maybe not everyone is. So I'll start with a very brief recap of the history, and I guess Jim can correct me if I say anything wrong, because he definitely knows the timeline better than I do. Um, but anyway, okay. So let's start from the shuffle theorem, which is essentially this identity here. Nabla En is a sum over dict paths, labeled dict paths of size n, q to the dim of the path, t to the area of the path, right? And then monomial associated to the labeling of the path, and then maybe we should say what all these things are. So nabla En is a symmetric function with coefficients that are positive polynomials in Q and T. Maybe we don't got too much into the details of the story of nabla and whatnot, but nabla is a very important operator in this symmetric function story. It's diagonal in the Macdonald polynomials. It's related to the diagonal covariance and all this story. But for the time being, let's focus on the combinatorics. So what the statement says is that this thing is actually a generating function for some set, which is the set of labeled dict paths. I guess everyone knows what a dict path is, but let's draw one. Is this fine? Yeah, the square, amazing. So we have a lattice path on an n times n integer grid with labels on associated to vertical steps so that columns are strictly increasing. Yeah, put a 5 here. another, an 8, 9, something like this. We can have repeated labels, whatnot. The area is very simple. It's just the number of squares between the path and the diagonal. So the area of this gadget is 11. I hope. The monomial is just the product of the variables associated, like associated to the labels that appear. So in this case, we have x1, x4 squared, x5, x7, x8, x9. And the div is the number of pairs of labels that are either in the same diagonal with this inequality here. So the lowest one is the smallest of the two, or in two consecutive diagonals with the one below that is on the upper diagonal and it's bigger than the other one. So I guess these two that I drew, no, there's a third inversion here. And I guess it's not all at all. There's another one here. So what's the name for this gadget? Name stands for diagonal inversions. There's one inversion here between this 4 and 5. They're in the same diagonal and 4 is smaller. There is one here, 7 and 5. 7 is one diagonal up and it's bigger. There's another one here. 7 is smaller than 8. It's in the same diagonal. And another one here. 4 and 8 are in the same diagonal and 4 is smaller. So if I counted correctly, there's 1, 2, 3, 4. And that's pretty much it. I mean, this is saying a lot of things. This thing is a symmetric function. It's not clear at all from the combinatorial definition. Like, why would this sum be symmetric? It's also sure positive. It's also very much not clear from the combinatorial formula. Another thing that's very much not clear is that the coefficients, the say monomial expansion, sure expansion, whatnot, are actually symmetric in Q and T. It's also extremely not clear from this formula. I mean, we don't even know how to prove it, even in the most simple cases. Combinatorially, the algebra, like this gadget, we know very well, and we know it's sure positive, it's symmetric, and it's Qt symmetric, and so on. This gadget, like we don't know it from the combinatorics, but we can deduce it from the algebraic side of the expression. So the statement here dates back to 2003. Jim, am I right?
I think that was right around there, yeah, 2003, or maybe a little later, 2003, 4.
3, 4. Okay. And then the proof, it's from 2015 by Carson and Mallet. So, I mean, it's been open for quite a while. But that proof was not the end of the story, it was rather the beginning of it. Because right around the same time, well, Jim, Andy, and Jeff Remmel gave another conjecture. It's very similar to this one, involving a slightly different expression. Let me write it this way. And we have a very similar formula. The path of size n, but with k decorated braces. And then again, to the dim, t to the area, some monomial. And also almost the same thing, but with k decorated valleys this time. Same expression. So I'm just copy this figure here. Right. Okay. So we should copy twice actually. We have two formula. This is still 2015. So what's rise? What's valley? Rise is just a north step preceded by another north step. So we have, say we set k equals 2 here. And contractible valley, maybe we should change this picture a little bit. Is an east step, a north step that's preceded by an east step with a condition. And the condition is that if there is exactly one east step, then we should have this inequality. So, I mean, we can contract the valley and still have an increasing column. If we have two or more east steps, then everything is fine because we contract this step here, but we still have valid labeling because the columns don't touch, they don't interact. And these decorations change the statistics in the sense that like the decorations on the rises change the area. You ignore the area in the rows containing decorations. The decorations on the valleys change the div. This is maybe a bad example, but what you do is you ignore the diagonal inversion so that the bottom label is decorated. And then you also subtract 1 to the dim for each valley you have. We can show that this is still positive. And this statement here is now a theorem, uh, proved independently by multiple people now in many, many ways. The first proof is that the Ellit, which uses a refinement that gonna appear later. It's important for our talk. Then there's uh, the paper. No plus, just 5 people. The beautiful series of papers by Blasiak, Heyman, Morse, Pohn, which is our host, and Sillinger that actually proved proved the extended version of this. Like they both proved something stronger, but in two different ways, like these two groups of people. And then there's another proof by Gillespie, Gorski, and maybe with a Y, and Griffin, which uses the rational shuffle theorem by Mellit, which is some sort of like version of this on a rectangle. We're gonna see it soon. And like via combinatory argument that we'll also see later in this series of talks, they managed to reprove the Rice version of the delta conjecture. There's also other proofs around, I'm pretty sure. I maybe don't want to list all of them, but I think there are some others. Like this is now the thing, like everyone many people have a different proof, which is kind of impressive because it still stayed open for quite a while. And so this is for the Rise version. The Valley version is good. Just here is completely open. Like we have pretty much no idea what's going on there. Like we don't even know how to prove that this guy here is a symmetric function. There's very little progress. Like there's some special cases, like with Michele D'Addario, we proved the Schroeder case of this thing. So when you have some special labelings, uh, there's some conditional results on this, but yeah, this is pretty much widely open. So I will really be happy if someone managed to get a proof of this. But let's go back to our story, there's another, well, there's a plethora of results in this fashion, and another one that we will need is the rational shuffle theorem. Let me call it EMN, the symmetric function. And then again, we have the same gadget, the same statistics, the same monomial. And now our paths live on an m times n rectangle. So we have stuff like this. In this case, we have, what is this? N is 6, M is, I'll choose this, 5, 9. Okay. And this symmetric function here arises from the elliptical algebra somehow. There's a bunch of like operators that transform symmetric functions into other symmetric functions. And we can recover this gadget from the story. Again, I don't want to go too deep into details here, but I mean, there are ways to build this symmetric functions here. And again, we have our labeled objects. This, the area is still the area. It's what you expect to be. I guess this is it. So in this case, there is 7. And for the div, maybe it's time to give an actual formula. There are many ways to state this, but I guess what I like to do is let me call Wi the label in row I and AI the horizontal distance between, um, well, it's easier if I just draw a line here. This distance here, like the distance from the beginning of the vertical step in that row and the diagonal, the main diagonal. So let me call temporary div of y the cardinality of the sets of pairs ij such that I um what is that? AI I is smaller in the lexicographical order than AJJ, smaller than AI plus 1 I, and WI is less than WJ. So when this condition holds, we say that like the step I attacks the step J. Let me write it this way. So I attacks J. And then when this happens, um, we count the pair for the temporary name if we have this inequality here. It's all good so far? Am I being like too boring? I mean, saying only things you all know, or am I going too fast? Any kind of feedback?
So just to be clear, your AIs could be non-integer, right?
It could be non-integer. Yes, exactly. Thank you for the remark. And actually, I mean, in the square case, what happens is that the AIs are all integers, so we have AI is either equal to AJ or AJ is equal to AI plus 1. So that's why we have the condition here or of being in the same diagonal or being shifted by one diagonal. In this rational setting here, we can have like fractionary, we can have rational distances. So And indeed, there is an even more general setting, which you don't even need rational. You can just like take any kind of slope, and that's what this gang here actually proved. So that's the thing, and then there's a correction to apply that depends only on the path, not on the labels, only on the shape, which I like to draw this way. So we have some steps here, some step here, and we want one step to project into the other, meaning that if we draw some lines that are parallel to the main diagonal, so these lines are not really parallel even with each other, but bear with me, I'm not great at drawing. Then we can see that like what we call the diagonal projection of this step here falls entirely into this step here, or vice versa. We can have something like this. We can have one vertical. Well, should draw this thing better, but I'm really terrible. Yeah, this is not exactly there. Maybe this way it's easier. Okay, something like this. And one of the two counts with a plus sign, the other one counts with a minus sign. Now I never remember which is which. Um, Maybe I should check. Give me a second. So I think these guys count with a plus. These guys count with a minus. And I think I also screwed up this picture a little bit because I actually wanted, yeah, sorry. I think, yeah. Um, Let me change this picture a little bit, sorry. I wanted the opposite uh thing. It's the same, but like this should happen like outside the path, not inside. So something like this here. And yeah, I should switch these two as well. Something like this here. Oh, apologies. So this thing should happen like outside the path, not inside. So the path is going somewhere like this, something like this. I don't know, and here as well. So we count the projections of these things. So like some, yeah, the horizontal step is below, not above. And like, okay, when this thing is a square, this never happens because we want the projection to be strictly contained in the step. And actually we take them open below, closed above. So yeah, this never can never happen if this is a square because the lines are just parallel to them in diagonal and the projections all have length one. But when the slope is not a one, we can have these two cases, and it really depends on whether the slope is positive or negative, greater or smaller than one, right? Like if here in this case we must have m greater than n. In this case, we need the opposite inequality. And so, depending on the path is wide or tall, we get different, we need to add or subtract something to the dim to get to this dim to get the actual dim of the path. And the thing that I believe made this difficult for the this rational extension of the delta conjecture is that there are more summands. Like both of these things can kind of happen. We'll see it later, why and how. So sometimes you have too much dim, sometimes you have not enough dim, but that can happen in the same size, and this is kind of throwing people off, I guess. That was one of the difficulties we had to deal with. Um, so okay, so that's pretty much the story before I even started like working on this problem. Like we had, well, the shuffle theorem was proved before I even started my PhD. And then when I started it, we started like this, it was 2016, so I started working on this conjecture here. And with my advisor and my academic sister Anna, we made like I would say good progress on the RISE version. And what we did was to introduce the theta operators. So for those of you who are familiar with symmetric function, the definition is this thing. Theta f applied to G, where f and G are both symmetric functions, is phi of f statistically evaluated in x over m, phi inverse of G, where m is 1 minus q times 1 minus t, and pi, I believe we can write it as um, this series here. Hmm. And this was very useful when trying to attack the delta conjecture because what Carson and Mellit actually proved in their paper was the so-called compositional refinement of the delta conjecture. So this is a very bad example because the path never touches the diagonal, but if we have a path like this, say, this touches the mean diagonal a bunch of times, and we can associate it to a composition, which in this case would be 3, 2, 3. And Jim with Jennifer Morse and Mike Zabrocki conjectured that like if we restrict the sum over paths with this fixed composition, then we should get nabla applied to C alpha, where C alpha is a symmetric function that's indexed by compositions and such that the sum over all composition of n of C alpha is none other than En. So this was like a really a game changer in this story of the shuffle theorem, this refined conjecture here, because that's what allowed Carson and Melli to find a recursion for these gadgets here, and then eventually prove the shuffle theorem. What we managed to do during my PhD was to rewrite this gadget here, the symmetric function, generating function of the shuffle in the delta conjecture as theta ek applied to nabla e n minus k. And the problem is that here, if you replace En with C alpha, you don't get any positive. Like this delta operator applied to C alpha just gives some negative signs, some fractions, like it's not very nice. But here, if you replace this instance of En with C alpha, then you get something that's actually positive. And this is like the correct refinement of the right version of the delta conjecture. It refines the delta conjecture here in the same way as this refines the shuffle theorem. So we have this compositional version, and that's actually what Carson and Mellit proved in 2015. Sorry, that's what that Darian Mellit proved in 2021. Um, this compositional delta rise delta theorem. All right. So we introduced these objects in 2019, 2020. I was just out of my PhD, and I moved to Montreal for a postdoc with François Bergeron. And he told me about this rational story, like this story here. I was like, okay. I didn't know. Well, I mean, I've heard of it, but like he suggested to investigate this a bit more. Like maybe there's something more to it. Maybe we can do decorated version of this thing here. And we just introduced this very fancy operator. So I was like, okay, maybe we can just like do the very obvious thing and apply this theta k to EMN. And what I was hoping for was a formula like the previous ones. So I wanted big paths of size and plus k and plus k with k decorated rises, some div, some area, the usual monomial. Didn't quite work, but almost. So if here we set q equals 1, we sort of had something. Like we had our paths. Something like this. We had our decorated rises. But then the diagonal was kind of weird. So what's the size of this thing? It's 4 plus 2 times 7 plus 2. So it's 6 by 9. But now I really should think of it as 4 plus 2 times 7 plus 2, like not just 6 by 9. Because what happens to the diagonal here is that it goes up with slope 7 over 4 in rows where you don't have a decoration, but then it goes up with slope 1 in rows containing decorations. And I think I probably screwed up the picture, but it's fine. Is that 7 over 4 or 4 over 7? That's also very confusing to me. I guess 4 over 7. Yeah. Right. And there is sort of what we expect is the number of cells, whole cells between the path and the diagonal in rows not containing decorations. It's kind of less satisfying than like what we expected because the diagonal is not just straight. Like the diagonal actually depends on the path. It's not like you draw the rectangle, you draw the main diagonal and then draw a path that goes above it. The paths like really determine the diagonal. Like there's not an obvious way to say, okay, this is above the diagonal, this is not, because the diagonal actually depends on where the decorations are. It's not just some family of paths you can decorate or not. It's something a bit more weird. Um, and like for like despair, we couldn't find dim statistic for these gadgets here. Like we kind of suspect that they are off by a constant that only depends on the shape of the path, not on the labels. This is sort of what we did in a previous work with Giovanni and Roberto and Anna. Uh, but it was something. Like we managed to prove some special cases. We like stated the conjecture when Q is 1. And it kind of stayed there. Like it always bugged me. Like we should be able to actually find like the correct extension of this thing. So, oops. So when I saw the work by Gillespie, Gorski, by and Griffin, I was very excited because I thought, oh, okay, maybe this can be the key. What did they do? What they did was to use the rational shuffle theorem to prove the delta conjecture. And what they sort of did was to, well, maybe I can write the formula first. They applied the Schur function. I hope I'm getting the numbers right. I think it's n maybe. No, maybe it's n. Skewing operator to E n kn. So this thing has degree n plus k, if I'm not mistaken. So it's kn minus k minus 1 times n minus 1. So that should be k plus n. And this happens to be equal to, again, delta prime en minus k minus 1 en, which is also equal to eta k nabla en minus k. So they managed to sort of find combinatorial like relation between the objects in the in the delta conjecture and the ones in the rational shuffle theorem in the case where the height is a multiple of the width. So in this case, we have, say, objects like this. I don't know, this, which I believe it's 12 times 4. So in this case, we would have n equals 4, k equals 3. And then they interpreted this operator here combinatorially. So you expand this gadget here in the homogeneous symmetric functions, and then we sort of know what like skewing by an homogeneous symmetric function does because the homogeneous are dual to the monomials. And so they're just some sort of erasing some labels in some sense. And on these objects, you have like a dim statistic. You do this skewing. I will go into details like in a later lecture because this is actually very, very central to our work. And then you get something of size n plus k times n plus k. So you get a square with k that would be 3 decorated rises. Maybe this is not the exact picture, but doesn't matter. With the labels and all. And then you show that the dim of this guy here is actually the same as the dim of this guy here. That's sort of the core of the work. Maybe I'm oversimplifying. I apologize if I am. But it's actually amazing. And then when I saw this thing, I was like, okay, but like they're only using like a small part of the whole rational shuffle theorem. Like they're only restricting to this case where the height is a multiple of the width. But the argument sort of still seems to work in general. So if we put something else here, something more generic, then maybe we should fall in something that's like rational version of this delta conjecture, which gets some rectangle here with some decoration. So the first thing I tried to do, well, first is to understand what to actually put here. And the claim is that we want Sm minus 1 to the k minus 1 per E m n plus kn. This is sort of more generic. Like we tried several things. Like it's not very obvious what like how to split m and n, but in the end we found this one. This is the expression we really want to focus on. And my hope was that this would have been equal to this gadget here. I mean, the degree is the same, which is something. Is it the same? K minus 1, maybe. Yeah. Yeah. No, sorry, Kn. Sorry, this is fine. The degree of this gadget is n plus k. And if that was the case, then I could use the argument like to transport the dim von rectangular objects to this decorated objects and then finally have a statistic for that thing here. But this was extremely false. Like this is not the case at all. Nope. Nope. Sad. So we were a bit disappointed, but not whole hope was lost because actually when we restrict to um well some scalar product, say we do HD E n plus k minus d, some hook, then this is the same. I think maybe oh sorry, wait, I think this is false, but not by too much. This is still false. But we can do a little trick here and just switch M and N. And now this holds. So what is this suggesting? So in this Schroeder case, these two are actually the same. And this is sort of like saying, okay, but actually you should switch M and N somehow. Of course, we can't have this equal to this because they don't even have the same degree. Like they're not really not the same. They don't have the same degree, so they cannot be the same symmetric function. But the fact that this scalar product was the same was saying something. And here, what is happening, right? We have our paths. Maybe I should just copy the picture from before. Yeah, this gadget here. And this scalar product here is saying, well, just ignore the labeling. Maybe we can do d equals 0. Like just to simplify a little bit, doesn't matter. D is not very important. D is just the number of, say, decorated peaks, but let's forget about D for the moment. Set D equals 0. What this is saying is just forget the labels. Like just take the objects as they are, no labeling at all. And now, like, there is some sort of symmetry, right? Like we can flip this picture. Can I actually do this? Let's copy it again. And let's see if I am able to flip this thing. No, no, no. Doesn't matter. Whatever. I don't think I can do this. Whatever. I mean, I kind of want to flip this one. Okay, let's just redraw it. It's easier. We can just reflect along the anti-diagonal. Or 1, 2, 2, 2, 2 again. No, just 1, 1. I think it's like this. And now we have the equations on false. And well, now there is some hope of like recovering thing, right? Because, okay, we said this is not the same as this because the degree is not the same. But here we're labeling the vertical steps. So if we flip the picture, now we still label vertical steps, we're actually changing the degree. And so what this is saying is that this thing is actually counting these objects. So we don't decorate rises, but falls. And this actually change like the picture. When m is equal to n, everything is the same. when we're on a square, there's an obvious symmetry between fall and rises. We can just like draw these diagonals here, and every fall, every rise corresponds to a fall. So this goes here and this goes here. Just follow the diagonal until you hit the path again. And everything is bijective. The falls, like the decorations, don't change, don't affect the div at all. Remember, like in the delta conjecture here, like the decorations on the rises change the area, but they don't affect, they have no effect on the div. So you can't really distinguish fallen rises. Like they're kind of the same in this picture here. They play exactly the same role. There's no difference at all. But when you switch to the rational world, there is a lot of difference because, well, even the diagonal changes. Like now you go, like the places where you go, you break this diagonal are different. The distances change, like everything is different. And it's really a different family of objects. And these are the objects that are counted by this symmetric function. Um, So I want to mention like this identity is conjectural. I don't believe it's too hard to prove this symmetric function. Well, polynomial identity, I guess, because there's scalar product, there's no symmetric function involved. Um, but I would like to see a proof of that. We sort of ignored it at the end, like we wanted to have the paper out. So it's okay, we'll leave it as a conjecture and then think about it later, and we never did. Um, but yeah, this thing is really saying something. Like we sort of related these objects to this expression here, and here we can actually do the trick by Gillespie, Gursky, Griffin. We can like use the combinatorial argument and get into objects that look like these and find the dim statistic on these ones. Um, so that's pretty much what we know. Oh, okay. Yeah. I read the chat comment by Sean. Yeah, the identity was um this identity, I guess, was already known by Blazek, Heyman, Morspoon, and Sillinger in their papers. So that follows from their work, and what GGG did, again, correct me if I'm wrong, was to like find this combinatorial interpretation of this identity that actually reproves the delta conjecture. Yeah, so we built up on that, and well, eventually gave a dim statistic for these guys. And I think we really hoped we could do was okay, but if for these objects we sort of have a temporary dim statistic and we only miss a correction that depends only on the shape of the path, not on the actual labels or anything, then maybe we can use the correction that's prescribed by the like symmetric path. This unfortunately fails really bad because well, it also fails in the square case. Like if I flip a big path across this diagonal here, the dim changes. Even if I don't have any labels, I just count like the attack relations, they're not the same. So I can't use the correction here to get the correction here. They're really different object. The statistics are really different. So we can't do that, unfortunately. Um, I don't think there's a lot of time to get into details now, but we have a lot of lectures to do so later. I just wanted to give you an overview, but I want to mention one more thing, which I want to get back to this picture here. So yeah. So as I said, the temporary dim is sort of the same. You just count like the attack relations and with the same definitions. And then you have to find this correction. But now, when you have decorated falls, streaks like this sort of count as just one big step. So to see what I mean, well, one of the interpretations we had was, well, this, okay, these count with a plus, these count with a minus, and that's still the case. But then also stuff like this counts with a minus. So we still have vertical steps that project onto horizontal steps, except now the horizontal steps are bigger. Like when you have a streak of decorated falls that's preceding a horizontal step, you just take all of them as a one single big step. And so you can have both stuff like this and stuff like this, because you're not restricted anymore by like these slope can be like low, but since these steps are long, you can have one vertical step that projects into onto one of these. And there's also one extra correction that involves decorations only, which is you have something like this, open to the left, close to the right. And then any kind of horizontal step, decorated or not, that projects into it. Just the left end point. All this stuff here, all of these things counts with a plus. And another thing I should mention is that, yeah, I'm drawing these lines straight, but they're not straight. Like they're parallel to the diagonal of the path. And the path, like the diagonal, is really not a straight line. It's a broken line. It's like, and by parallel, I mean like they're vertical translates. Like you can move it above and below, but like you have to translate it like to keep this endpoint on this line, this endpoint on this line. So this is what we mean by diagonally project. And I guess one last thing that can help sort of help visualizing what we're doing, it's not crucial. Like we can bypass that entirely and still have all the results and everything. But it kind of helps to see the picture this way. Let me copy this one. So this is an idea that we discussed with another friend of mine, Matteo Migliorini, which, well, then did not participate in the paper, but this insight came while discussing stuff with him, so I wanted to mention him as well. And the thing is, we can make these things disappear with a little trick, which is what we called ENS representation. This is not École Normale Supérieure, but it's just east, north, and south, meaning that what we can do is whenever we have fall, we can actually make it fall, like go down instead of east. So we can have stuff like this. And now what happens is that like, well, the diagonal is straight again. So this thing starts from 0, 0, ends in MN. In the area, well, what's the area here? It's, well, this, I hope. And it's exactly the same area here. But now it's like it's a lot easier to see. You don't have to disregard anything. You don't have to like ignore stuff or like draw this horribly broken line. You can just draw your honest diagonal on the m times n size thing. Um, I should have collapsed something else, I think. No, yeah, that's fine. and just add a bunch of south steps, the number of south steps being the number of decorations. And then all the paths you can draw that stay weakly above this line, they correspond to these gadgets here. And here, things are a little bit easier to see. Like the diagonal is straight, the projections are like honest projections, the labels are just what they are, the area is what it is. And this helped, like at least in like writing the statement properly and like checking that everything was correct. Having this way to see what we were doing was extremely helpful. And it's kind of like it's very easy to miss when you're only looking at square objects because it's not really helping. Like when you're a square, that this line is just straight. Like you don't see this breakpoints, you don't see this anomaly in rows with columns, I guess I should say, with decorations. But when you work with rational things, it does make a difference, and this way makes everything a lot cleaner. Okay, I guess I talked enough for today. I didn't go into the details of anything so far. I plan to do so in the next few lectures, but I wanted to give you an overview and like an insight of like what the thought process was to get to the actual result. I'm happy to take any question.
Well, let's thank Alessandro for that excellent big picture there. Yeah, any questions? Uh, oh, so I see in this final diagram you have just north steps which can reverse themselves.
Mhm.
Like, and could you add in like east steps which can reverse themselves? Is there
I
that any
mean,
kind?
we considered it because when you do like when you look at this picture, that's pretty much what's happening, I guess, right? Oh, I think maybe okay, maybe it's not super clear in this picture here, but like it's not necessarily going down immediately. Like you can if you start from a streak like this, then you go like this, right? No, sorry, this is so yeah, this because your step here, this one here, so they don't
Mhm.
like reverse themselves immediately.
I see.
But yeah, that's actually what we realized with Matteo. We were still working on this picture, and he suggested that like instead of going north here, we can go west, and then we solved the same problem. So we thought about that a little bit. Didn't really go anywhere. We still have the same problem because really these two pictures are like entirely equivalent. Like um this makes everything nice and easy to see, but it doesn't change the combinatorics at all. So the problems we had here, we still had with west steps. But then when we translate it to this picture here and false, and now the south steps are a bit easier to see. Also because here, like you're labeling the steps here, right? So when you go west, you still have to label the step, and it's kind of odd. Like you have these labels that sort of go all around the place. Well, here you're just labeling north steps. And I guess that's the main difference between these two pictures is that here, like on the right, labels and decorations like talk to each other a lot and they kind of interfere with each other in some sense. Well, here you have the labels on one like direction and the decorations on the other, and yeah, and it's easier to like deal with them. So yeah, we consider like west steps, but mm, that didn't help much. What we didn't try to do is to add both of them at the same time. So maybe
Yeah,
that's a thing to think about. Yeah.
kind of an interesting historical comment. I think my
Mhm.
first PhD student was Chung Wei Song. He was
Mhm.
studying the combinatorics of the QT Schroeder. And
Okay.
in connection with that, he introduced paths, this is in the square case, which have this pattern where you can go up, across, and then down, like you did here. He said that
Okay.
that's a cave. And he showed that the number of such paths is in bijection with permutations.
Okay.
But in his
Let's
paths, you
see.
can't go like up and straight down again.
Okay.
Yeah. Anyway, just an amusing fact. Okay.
Oh yeah, I guess I have to mention, sorry, that yeah. These are like decorated falls. So when after you go down a bunch, you have to go east. You can't go up again.
I see.
So you cannot go, yeah, like this. Not allowed.
Okay. So any other questions? All right. Well, look forward to Thursday's talk. Oh, by the way, uh, so these things are being recorded and we're putting, Anna's created a YouTube channel for these, and there'll be links on the IPAC webpage within the next day or so to recordings of the talk and other future lectures and also lecture notes. Okay. All right. So anyway, we'll thank the speaker again and see everyone on
Thank you.
Thursday.
Yep.
So.
Bye.